Kelvin temperature scale. This video will explain the definition of temperature on the Kelvin scale and how to convert it to Celsius, vice versa. Additionally, this video will discuss how temperature is related to changes of states through the heating and cooling curve of water. Let's begin. Temperature. IB defines temperature in Kelvin as a measure of average kinetic energy of particles. This definition aligns with the kinetic theory of gases, which states that the temperature of a gas is directly proportional to the average kinetic energy of its particles. Throughout the video, I will highlight important key IB vocabularies in yellow. It is crucial for students to learn and memorize the definitions of these words because they can be tested on both the Paper 1 and Paper 2 external exams. Students might not be familiar with the SI unit Kelvin for measuring temperature. Unlike Celsius, which is commonly used in everyday life and weather reports, Kelvin is the unit used in scientific contexts. The SI unit Kelvin is based on absolute zero, the theoretical lowest possible temperature where particles have minimal motion. Students should know how to convert between the two SI units. Kelvin starts from absolute zero, 0 Kelvin, which is equivalent to negative 273.15 degrees Celsius. Let's practice converting between the two SI units by solving some examples. Question 1. The temperature of a reaction is 125 degrees Celsius. Calculate the temperature in Kelvin. We know that the temperature of the reaction in degrees Celsius is 125. From the previous slide, we know that the temperature in Kelvin is equal to the temperature in Celsius plus 273.15. So if we substitute the temperature of the reaction in Celsius, we can say that the temperature in Kelvin would be equal to 398.15 Kelvin. So that would be the answer for question 1. Let's look at another question, question 2. A gas cylinder is stored at a temperature of 298 Kelvin. Calculate this temperature in degrees Celsius. So the gas cylinder is stored at a temperature of 298 Kelvin. So the temperature in Celsius would be equal to the temperature in Kelvin subtracted by 273.15. So if we substitute the temperature in Kelvin, we'll get 298 minus 273.15, which is 24.85. So the temperature in Celsius can be converted to 24.85 degrees Celsius. Do you remember the changes of states from the previous video? This video will go one step further and explore how changes in temperature is related to the changes in states through the heating and cooling curve of water. First, let's look at the heating curve of water. The heating curve of water is a graphical representation that shows how the temperature of water changes as it absorbs heat, illustrating the phase transitions from ice to liquid water to steam. Starting with ice at a temperature below 0 degrees Celsius, the curve initially shows a rise in temperature as heat is added, causing the ice to warm up until it reaches 0 degrees Celsius. At this point, the temperature remains constant as the ice melts into liquid water, even though heat continues to be added. This flat section of the curve represents the latent heat of fusion, the energy required to change ice to water without changing temperature. Once all the ice has melted, the temperature of the liquid water begins to rise again as more heat is added. This continues until the water reaches 100 degrees Celsius, where the temperature levels off again. During this phase, the water undergoes vaporization, transforming into steam. The energy added during this flat section is the latent heat of vaporization. After all the water has vaporized, any additional heat will increase the temperature of the steam. Conversely, the cooling curve of water demonstrates the temperature changes as water releases heat, reversing the process from steam to liquid water to ice. Starting with steam at a temperature above 100 degrees Celsius, the curve initially shows a drop in temperature as the steam cools. Once it reaches 100 degrees Celsius, the temperature remains constant while the steam condenses into liquid water, releasing the latent heat of vaporization. After all the steam has condensed, the temperature of the liquid water decreases steadily until it reaches 0 degrees Celsius. At this point, the temperature again remains constant as the water freezes into ice, releasing the latent heat of fusion. Following the complete freezing of water, the temperature of the ice continues to drop as it loses more heat. This cooling curve highlights the energy released during phase changes and the periods of constant temperature associated with the phase transitions. The heating and cooling curves of water demonstrate the relationship between temperature changes and phase transitions, highlighting periods where temperature remains constant during melting, freezing, condensation, and vaporization. These curves illustrate the significant energy exchanges required for water to change states, emphasizing the unique thermal properties of water. That's it for this topic. I hope you enjoyed this video, and if you want to see more, don't forget to subscribe to my channel and hit the like button. Thanks for your support. If you have any questions, comment below.